by a hands-on session. So basically for that hands-on session only, I've shared couple of links. Already Rahul has shared it in the chat box. So for that second link, please make sure you sign up with any of your email IDs so that if anybody wish to do that hands-on session along with me, you can do that, right? So talking about ML or data science or AI, these buzzwords are kind of relevant or has become more relevant in the last 10 years or so. So we live in a world whose rules and procedures are governed by data and algorithms. Right from the moment we wake up till the time we sleep, we either consume or generate data. So, so obviously, this is something which has kind of completely changed the world in the last 6 7 years. So the basic outline of the talk will cover a little bit of basics of ML so that I can just make sure that you will understand what I'm or you it will make sense on what I'm talking. And also we'll see few aspects about how what exactly is interpretable AI and how do you actually after building the ML model, how do you make sure that your model is fair, transparent, and um, uh, basically accountable. And also we'll just see few aspects of uh, how exactly you can measure interpretability and explainability of a machine learning model. And then we'll just see what are the future aspects and also what are the future relevance of these kind of techniques, right? So just to begin, all of us know that if you are thinking about a traditional programming such as C or C++, how exactly it works is that you will have certain step-by-step procedure. You write the flowchart or algorithm for that. Then on that, you put your data and basically you will get the output. So right from our maybe undergraduate days or like whenever we started learning programming as a or any of the programming language, this is what it has been happening. But when it comes to machine learning, it is something the other way around. Here, you give the data, you give the output, and you ask the machine or the computer to find out the patterns in that. So what happens over here is in a traditional programming language, if you have a couple of numbers and you write a program to add that couple of numbers, even if you run that program 100 times, still you will be getting the same output because some of those two numbers are never going to change. But when it comes to machine learning, you build a model and you compute the accuracy of that model. In every iteration, you will be getting different accuracies. So there are scientific methods to kind of counter that, or in other words, to solve that issue. But still, this is actually a reality where you run the program 100 times, you may get 100 different accuracies, right? So in a way, I can say that machine learning could be sort of a magic, but I would like to call that more like a gardening thing. So usually, how do you do gardening? You just plant few seeds, you water it, and you expect that it sprouts and come as a wonderful sapling, right? So that is the expectation. But unless and until it comes out, we don't know what is happening inside, like down under the soil, right? So that's why I would like to kind of relate this to gardening. So here I can say that seeds are like algorithms. You have dozens and dozens of algorithms which can do prediction, which can do classification, which can do clustering, these sort of things. And here you have data as nutrients in the soil. So, and also like, you can assume that you are the gardener and plant is nothing but the program which basically gives you some sort of pattern, right? So in a way, most of the ML models, if you consider, there is some sort of black box nature embedded into all these sort of models. So which means that sometimes it is difficult or impossible to explain what is going on inside the model. So you take any application, it will have some sort of background or uh, some sort of reason or some sort of some sort of reason to what I just said now. That is, it is a black box. So, for example, if you think about any e-commerce application or any sort of recommendation system, so most of the time, on what basis it is giving that recommendation, it might be kind of abstracted, both from the user level or even from a programmer level as well, right? So obviously, the use cases of AI ML, I'm sure in the previous sessions you have come across. So I'm not going into those aspects. But one aspect is that there are thousands of ML algorithms available, and there are hundreds of new algorithms coming up every year. And usually, every machine learning model has three components. So usually we say it is all about representation, evaluation, and then you keep optimizing that model, right? So any ML model or ML algorithm you take, these are the three general things. So I have been for quite some time talking about the word modeling and all. So what exactly is modeling? So this is a little bit tricky question, because modeling as per the dictionary meaning, you can say that you're trying to represent some aspect from the real world. It's not the actual thing, but some sort of representation. So that you call as model. So it could be anything, even say for example, you can have a model in a completely different context, or not only from a machine learning perspective. So, but in all these aspects, in one way we can say that it is a representation which is trying to mimic some real world aspect. So whether it is maybe if you are looking at the blueprint of a building, right? In those cases also, a blueprint or a plan of a building can also be called as a model. But when we come to ML, the model what we are talking about is a little different. So here I'll just share a whiteboard so that it makes more sense. Just give me a second. Just a second. So this is the example which I just mentioned. You have a blueprint, even that can also be called as a model. Or if I have a small sort of like diagram of this sort, right? Even that can also be called as a model. But again, I'm saying it is not from an ML or AI perspective. In general, all these things could be called as model, right? Now, if I'm taking another example, so you have a picture of an aeroplane right here. So this aeroplane, if somebody is asking like, how does an aeroplane looks like, then maybe this sort of a picture can make sense, right? So the person can understand, okay, this is what an aeroplane looks like. But what if I ask a question saying that, can you give me a model which can do some sort of safety testing on a flight or on an aeroplane? So then with this model, you cannot do any sort of thing. So for that, you may have to go for a model or a diagram which will show the internal working of a particular flight, and accordingly, more aspects or more features of that problem or features from a safety perspective should be shown. So otherwise, whatever model you are seeing here, that can only tell how a plane or aeroplane looks like. It has got nothing to do with uh, something like safety test, right? So the same goes for here. For example, if someone is asking, can you do a sort of stress testing on this building, this sort of a house, right? So uh, this basically gives you how a house looks like, but it may not be able to this building. So the point which I'm trying to tell here is, even if in real world also, whatever model you are seeing, a model which can convey one sort of, or which could be helpful in one scenario may not be very much helpful in the other scenario, right? So from use case to use case, or from the kind of problem you are dealing with, models can vary. So the same goes for any sort of mathematical model. So what you see on this on screen is y is equal to mx plus c, which is a very basic formula which you have seen right from your school days. So even this could also be called as a mathematical model. So usually here what happens is if I want to know the value of y, I can plug in different variables into this model. So here I have a formula which help me to kind of get the value of y. So that's a very simple formula. So usually this formula can also be called as a mathematical model. So once you have data put into this sort of a mathematical model, such kind of models are known as statistical model, which is the basic thing for all machine learning models. So you have some sort of a formula and you have some data, then that can give you a statistical model, right? So which means that usually we assume that you have a problem, you put that or give that into the model, which is for the time being, you can think that as a magic box or like a gardening thing, and you give that and you get the corresponding output. So for any model, you have something called a randomness and uncertainty embedded in that. So that is something which is universal. All model has this sort of randomness and uncertainty. It may not be as simple as the formula which you see here, y is equal to x plus 2. So every model will have a definitely a formula, but that formula is gonna vary from model to model. So once you have this formula and data, then that will help you to build a model, right? So usually whenever you say that you have some data, then you have some sort of an architecture which you call as a math model, and then you have the formula. These three will give you something called ML model. So why I talk about these things is that, so there are various aspects to this. So which means that when you say talk about a formula, there are certain variables or features which are dependent variables, and there are certain variables or features which are independent variables. So out of that, how do you know that which are all the independent variable and which are all the dependent variables? So imagine that you want to find out the relation between price of oil versus the consumption of oil. So you want to find out the relation between these two variables. So assume that your uh, uh, let's assume that the price of oil is the target variable and consumption of oil, let it be the dependent variable. So in any sort of these formula, you will have dependent as well as independent variables. So I'll just give you another example. I'll just write down here, maybe 1 second. Yeah. So for example, if you want to compare these things, I can say that whatever that is on the left hand side, let that be the response variable, and whatever that is on the right hand side, let it be the explanatory variable, which will in turn uh, give something to this response variable. So the earlier example also, y is equal to mx plus c, I can say that y is the response variable and whatever that was on the right hand side is the explanatory variables. So for any sort of model, this is something which kind of which is kind of common, right? So again, we'll move back to the slide. So in general, any ML model you take, this is how it works. So which means that you may have some sort of an let me just take the pointer. Yeah, some sort of idea, and that you with that you design the model, which means that you may have a formula, you may have some sort of I mean you will have the data, and then you may have your own model architecture, which could be some sort of mathematical model as well, right? So based on that, you do something called a training, and then you evaluate the model, whether it is accuracy is good or whether it is very efficient. So all these aspects you will try to find out. So I was told that already you had a session on ML basics, so I'm not going into those aspects like how it is to be done. So then you test the model performance, and then you interpret whether it is actually matching to your expectation. So this is how a usual modeling process works, right? So uh, if you think about these, there are different sort of models available. So yeah, so there are different sort of models available. So which means that right from, if you think about last 30, 40 years, there are hundreds of ML algorithms available. So all these things could be thought about as model architectures. So which means that to these architecture, you give a formula which consists of your response variable and explanatory variable. And accordingly, this architecture, I mean, you give the formula as well as the data to this architecture, and this is going to give you the sort of prediction or sort of classification which you are expecting. And after giving that, how do you know that what you are getting is the right answer, or is it something wrong, or it doesn't make any sense? So to know that, there are a lot of evaluation metrics available, including uh, what you can see on the screen. So if you think about, I'm sure you would have heard about something called a confusion matrix. So from that, you can find out a lot of parameters, or I mean, a lot of metrics. So if you think about precision and recall, which is very commonly used in many real life applications. So for example, if you are doing some sort of medical diagnosis, and precision and recall can be used to evaluate the performance of a model in identifying maybe patients with a particular disease condition, or high precision indicates that the model is correctly identifying patients with the condition, while high recall indicates that model is identifying a large percentage of patients with the condition. So there are a lot of metrics related to this. Or if you think about things like mean square error, it is a very common loss function used in machine learning to measure the difference between predicted values and the actual values. So especially it is used in regression problems. So uh, or else if you think about things like entropy. Entropy is a basically a concept from information theory, which is widely used in machine learning to measure the uncertainty or randomness in a set of data. And there are various aspects to that, like KL divergence, also known as relative entropy, which is a measure of difference between two probability distributions. So there are dozens of measures which says that, hey, I'm going to evaluate your model and I can tell you whether your model is good or bad. So there are these many measures. And also, once you have these measures, we also do something called optimization of these models. So you can also think that as sort of a hyperparameter tuning. And uh, it's almost like a game where we have to find the best way to do something by trying out different combination of things. For example, you imagine that you have a bunch of toys and you want to put them in a toy box. So you have to figure out how to fit them all in that box in the best way possible. So maybe you can stack them in a certain order or arrange them in different ways to make them all fit. So now, let's say that you have to pack a kind of backpack for going to maybe office, right? So you have a bunch of books and maybe like things like tiffin box and all, but you don't want your backpack to be too heavy. So if you have to figure out which items to pack in what order to make the backpack as light as possible, all these things are known as combinatorial optimization, which is used to solve all sorts of problems like scheduling workers, routing delivery trucks, or designing efficient computer networks. So by exploring different combinations of choices and finding the one that produces the best outcome. So using that, you can solve complex problems and make things work more smoothly and efficiently. So there is also the other aspect known as convex optimization, which is a bit more advanced than combinatorial optimization. So, but I'll try to explain in a way that makes sense to you. So imagine that you have a big hill with different paths. So you can uh, you have different paths to reach to the top of that hill. So some paths might be steeper than the others, and some might be shorter or longer. Convex optimization is like finding the easiest path to the top of the hill. In this case, you can imagine that the hill is like a mathematical problem, and the paths are different ways in which you can solve that. So convex optimization helps us to find the easiest and most efficient path to solve or way to solve the problem by looking for the smoothest path, the one with no sharp turns or steep inclines. So in real world, convex optimization is used in all sorts of fields like economics, finance, engineering. So all these aspects. So it helps to find the best solution to a problem by minimizing the amount of effort or resources needed to achieve our goal. So in short, I can also say that say convex optimization is like finding the smoothest path up a hill, and it helps to solve the problem in the easiest and most efficient way possible. And also, there is another aspect. So all these things, remember, you build a model and then again you want to optimize that. So in that aspect, these are the various optimizations possible. So there is this thing called a constrained optimization, which is a little bit complex than convex or the combinatorial optimization. So uh, imagine that you are playing a game where you have to stack uh, blocks like a Lego blocks, right? So on top of each other, and you are asked to make a tower. So, but imagine that there are rules you have to follow. Assume that you can use only a certain type of block, and you have to make sure that the tower doesn't fall over. So constraint optimization could be like playing this sort of a game, but instead of building a tower, we're trying to solve a mathematical problem where you have certain rules or constraints which we have to stick to. So there are a lot of real world applications in again in computer science as well as engineering, finance, economics, etc. So uh, constraint optimization is like you have a game but you have a lot of rules which kind of restrict your movement, but it helps us to find the best solution while also making sure that we don't break any rules or exceed any limits. So, and also this is all about optimization. And at the same time, you also have different kinds of learning. So even though we are not going into the depths of these things, I'll just give a brief idea of like what exactly is supervised learning. So usually it is a type of machine learning where you teach a program how to recognize different things or like animals or shapes by showing examples. Like so, let's say you want to teach a program how to recognize different animals. You show the particular program lots of pictures of animals like cats, dogs, birds, and you tell the computer or tell the program which animal each picture shows. This is known as labeling, and from an image perspective. And basically, the program will use this information to learn how to recognize different animals. And then, if you show the program a new picture of an animal, it could tell us what is that animal. This is basically in a very peripheral level. This is what is supervised learning. When it comes to unsupervised learning, it is another type of learning where a program learns to find patterns and relationships in data without being told what they are. Imagine that you have a bunch of different toys, but you don't know which ones are similar to each other, and you just put the complete random images, and it just tries to group that to which group that toy might belong to. So there are a lot of real world application like say for example your shopping habits or your social media post to find patterns and relationships. So from all these things, the underlying things could be unsupervised learning. There is also something called a semi-supervised learning, where a computer or a program learns to recognize things by looking at both labeled and unlabeled examples. So imagine that you have a bunch of different fruits, but only some of them are labeled with their names, like apples or oranges. Semi-supervised learning is like using the labeled fruit to help you figure out what the unlabeled fruits are. Right? So this is really significant in many applications like language translation or identifying fraudulent behavior. So basically, it helps us to make predictions and decisions based on both labeled and unlabeled data. The other thing is reinforcement learning, where you make a program teach how to make decisions by getting rewards or punishments based on its actions. So it is like a pet training. So you imagine that you have a pet dog and you want to teach it how to do tricks. So when your dog does a trick correctly, you give it that as a treat as a reward. But if your dog does the trick incorrectly, you don't give the treat. So it's like instead of a dog here, you're making use of a program, right? So this is a very peripheral understanding or view about different kinds of learning. So I'm sure for quite some time you have been listening to me. So we'll take a very short 1 minute power break so that you can also take your eyes away from the screen. All right. So we'll move to the other aspect. Is all about like either you're I'm sorry. Yeah. So either you are talking about a certain domain and you have a specific problem and you also have some sort of task in front of you. It could be some sort of prediction, it could be finding the patterns, or it could be something totally different. So in all these things, you do this in an iterative way. So earlier I mentioned about modeling as a process. So in that also, you are trying to basically do these sort of things. Either it could be prediction or it could be some sort of classification, or usually these are the two different tasks which you make a ML model to do. So uh, just to understand how exactly a model learns these things, we are gonna make our brain as a ML model. So what you see on the right hand side, you have all these different pictures which shows the infected or basically slides which show that a particular cell is infected with malaria. And what you see on the right hand side, those are the samples which are uninfected. So I'm sure during your school days, you would have kind of uh, been part of a competition like where they'll take you to a room, you will see all these different objects kept on there, and then you come back to the other room and you write all these objects what you have seen in the other room. It's kind of a memory test. So similar kind of a test we're going to do now. So what you see on the left hand side, you have these small violet patches. So those are infected cells, but the clean things, all these things are kind of uninfected. So I'll just show you a sample. So can you tell me whether this is infected or uninfected? Maybe you can type it in the chat box. So the earlier slide, I have shown what is the characteristics of an infected cell, and over here, what it could be. Yeah, somebody said infected. I'll just wait for a few seconds. So all are saying infected, but unfortunately, uh, this is actually an uninfected cell. So we as human beings also, after seeing those images for a few times, like we thought that this small tinge here that could be infection, but unfortunately that is not a infected cell. So the right answer is uninfected. So we'll see one more example. Now what about this one? So this is more clear here. Yeah, somebody just said infected. Yeah, so here it is right. Of course, the cell is infected. And we'll see one more example. So here also slight tinge of violet is there. So the the point what I'm trying to show here is that even as human beings, we find it little difficult to kind of tell whether something is infected or uninfected. See those sort of things, right? So sometimes what happens is you have a lot of ambiguity in your data, and sometimes like even as human beings, we may make mistake, right? So there are a lot of challenges in machine learning, whether it is a image or whether it is a video or whether it is a text or whether it is a tabular data. In all these sort of data, you will have certain common challenges. So just to kind of talk few things about those challenges, I just showed these slides. So usually we say ML models are only as reliable as the data which is used to train them. So if you train your machine learning model on an incomplete data set, or on data with poorly selected features, or on data that doesn't accurately represent the population, uh, your model predictions will be obviously a direct reflection of that data. So as a result, ML models are often also referred as garbage in, garbage out models. So you might be thinking, even after building that model, you usually find out the accuracy you from your results, and then why we should say that it is garbage in, garbage out. So because what happens is the quality of the data is basically it depends on uh, or it is directly correlated to your model as well. So for example, if your data is not right, then obviously the model will also be a direct reflection of that data. So that can have a lot of effect on the model, and also it will affect your accuracy as well, right? So the other aspect could be data completeness. So assume that you're trying to build a model which is able to identify different sort of cat breeds. So you train the model on an extensive data set of cat images, and assume that the resulting model is able to classify images into one of the 10 possible uh, cat breeds. Say it could be a Bengal cat, it could be a Persian cat, and so forth. So your model, you got some accuracy such as 99%. So when you deploy your model into production, you find that in addition to uploading cat photos for classification, many users are uploading photos of dogs, and you are very much disappointed with the model's results because the model was trained only to identify 10 different cat breeds. This is all it knows how to do. So these 10 cat breeds are essentially the model's entire worldview. No matter what you send the model, you can expect it to slot it into one of these 10 categories. It may even do that with very high confidence. So maybe if you are a model, or if you are class, you if you had an additional class like not a cat, then maybe it would have been done better. So data completeness is also one aspect, and the other aspect is data consistency. So for example, sometimes you may have a lot of inconsistencies, a lot of missing values in your data, and also timeliness of the data. So these are very common things. So I'll go to the other aspect, which is more related to the topic which we are going to discuss. So as I mentioned earlier, in traditional programming, the output of a program is reproducible and it is guaranteed. But ML models, on the other hand, they always have an inherent element of randomness. So when training ML models, for example, there are models where you have weights associated with that. So ML model weights are initialized with random values, and these weights then converge during training as the model iterates and learns from the data. So basically, because of this, the same model code given the same training data will produce slightly different results across the training runs. So that is why you have things like cross validation and all. So this introduce basically, but this is a very big challenge of reproducibility. So if you train a model to 98.1% accuracy, a repeated training run will not guarantee you that it is going to give the same result. So this can really make it difficult to run comparisons across experiments. So there are this is one aspect, and also there is something called a data drift. So sometimes the kind of data what you're getting, it could change over time. So one example you can think about is if you are asked to build a model which can automatically classify news articles into categories like politics, business, technology. You give a news heading, and it is going to classify that into the corresponding class. So assume that you are building this model from the historical news articles from 20th century alone. So it is very likely that that particular model won't perform good on the current data, because today if you have an article with the word smartphone in the headline, probably if you are using the data from 20th century, the model will not have any idea about what is a smartphone, right? So this is what is actually meant by data drift. You would have uh, made the model on a sort of data, but later things have changed. You start getting new data, and the model is unable to understand what is that, right? So there are various aspects. I'm not going into all of that, but the main topic which we are going to see here is that uh, all models, whether it is small or big, there is some sort of inherent randomness embedded into that, right? So obviously, can we say that whatever prediction the model is doing, is it done on a fair manner? Or can we trace the predictions reliably back to something or someone? Like what could be the reason for this prediction? Or can we explain how predictions were made? Can we explain how the model works? So ultimately, if you can answer all these questions, then only you will be able to trust that particular model. So this is the aspect. So for example, imagine that you have a kind of a healthcare center that provides a service to from the blood sample. Usually doctor is analyzing the samples, and basically the doctor will tell whether the result is positive or negative, or the technician will tell, right? So here assume that this is the normal system, right? Now imagine that you want to convert this into a sort of uh, AI system. So obviously
Hello, Ebin. Hello. Am I audible, participants?
Yes, sir. This
Yeah.
audio is not.
hello,
Yes, sir. Yes, sir.
Yeah, Ebin.
hello.
Yeah, please. Yeah.
Yeah, I think by mistake the my mic went on mute. So can you tell me till what point you have heard? Hope
Sir,
I'm
it just
audible now.
started. Yes, sir. I think from the beginning.
From the beginning, in the sense, this interpretable AI, have you heard?
Ye- Yes, sir. From the next slide.
Yes, sir. Like the blood samples are collected and in the
Oh,
normal
that
system.
okay. There it got. I don't know how it got muted. Okay, yeah,
Okay.
yeah. So we'll take a look at yeah. So we'll take a look at one of the example.
Participant, please mute your mic. Yeah. 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 Please. Please, Ebin. Yeah.
Yeah, yeah. So we'll take an example of a, say, let's say you have a healthcare center. Usually, how it happens is you give the sample, a technician or a doctor will will go through that, and you have a diagnosis. Now imagine that you have AI for doing the same task. So the goal of this AI is to use images of blood smear samples with other patient metadata to provide diagnosis like positive, negative, or neutral with a confidence measure. So assume that you need to have like doctor in the loop to review the diagnosis, especially the harder cases. So thereby allowing the AI system to learn from mistakes. So for this sort of a thing, uh, imagine that you got something, and you can see here you have also the doctor in the loop, which can kind of validate whether whatever that is the decision taken by the AI system is right or wrong. So usually this is how a system which doesn't have AI, when it starts incorporating AI, this is how a system looks like, right? Now, assume that you are building an ML system based on this, like you have some historical data and you uh, build the model, you do cross validation or validation test, all these things, and then like you do it. So once you've trained the model, you validate it and you find out the performance of the model. And this process is quite iterative, right? This development process. And then you basically test the model. You switch over to the testing environment, maybe use a subset of the data called as testing data set, which is different from which is usually different from the training data set. And the objective is to obtain an unbiased assessment of the accuracy of the model. So here the stakeholders, in the our example, it is doctors. At this point, they would evaluate the functionality of the system and also the performance of the model on the test set. So this additional testing is also known as user acceptance testing, which is the final stage in the development of any ML model or any software system. So if the performance is not acceptable, then you go back to phase one and you tweak your model and you train a better model. So, but in case if the model is found to be really good, then you move to the stage of deploying, right? So in the deploying phase, we now learn the model in the production. I mean, we now deploy the learned model into the production system. So here the model is now exposed to new data that it hasn't seen before. So you will be getting new blood samples which you haven't seen earlier, and it needs to basically predict that. So uh, so this system is basically to diagnose whether it is positive or negative with the confidence measure. So, but this AI system does not safeguard against some common issues for which the deployed model may not behave as expected in the production environment. This is a common issue irrespective of the domain. Sometimes a model which was really good in your testing phase or in your test environment, once you deploy it into the real environment, or you have a system and you deploy it in that pipeline, sometimes you may not get results as expected. So there will be a lot of issues. So this is a something which is very common. You deploy it and then suddenly you feel that it is not doing the job which it ought to do, right? So there are some common issues like data leakage, which happens when features in the training, both development or test set or training or test set, unintentionally leak information that would otherwise not appear in the production environment. So um, for example, for this, I'd like to quote an example. There was a classic case study of data leakage in the Kaggle competition in 2008. So the objective of that machine learning competition was to detect uh, whether a cell has cancer or not, or whether it is benign or malignant on X-ray images. So one study showed that the teams that scored the most on the test set for this competition used a feature or a variable called patient ID, which was an identifier generated by the hospital for the patient. It turned out that some hospital used the patient ID to indicate the severity of the condition of the patient when they were admitted to the hospital. So in turn, right from the patient ID, it is possible to know the significance or there's a relation between the disease and the patient ID, which should not have happened. So this is an example of data leakage. So this is one reason where a model which has kind of played well in your environment is not doing good in a real environment, or after deploying it is not doing well. The other aspect could be bias, where the ML model makes an unfair prediction that favors one person or group over the other. So this unfair prediction could be caused by the data or sometimes the model itself. So there may be sampling biases in which systemic difference exists between the data sample used for training and the population. So there is a classic case study for this sort of a machine bias by the Compass AI system used by the US courts to predict future criminals. So this study was conducted by a firm called ProPublica, and ProPublica obtained the Compass scores for 7,000 people who had been arrested in US, or I think specific state. I don't remember the state. So using the scores, they found out that they could not accurately predict the rate at which a convicted person reoffends. So only 20% of the people who were predicted to commit violent crimes actually did so. So more importantly, they uncovered serious racial biases in the model, especially the black people were more in that category, right? So this is the second thing, bias. And third is known as the regulatory non-compliance. So if you think about the European Union or in the US, there are a lot of data protection regulation. So the General Data Protection Regulation of European Union, or more commonly known as GDPR, so they basically deals with how data is collected, stored, or processed by foreign companies. So they have certain things like right to be forgotten, where individuals can request the company collecting the data to erase all their personal data. So the regulation also contains aspects where individuals can challenge decisions made by an algorithm or AI system for using their personal data. So ultimately, it need to be compliant with all these aspects. And the other aspect is, as I earlier mentioned, drift or concept drift. It happens when properties or distribution of the data in a production environment has changed when compared to the historical data used to train and evaluate the model, right? So how do I build a model who can build or who can address all these challenges, right? So one thing is that there could be how did the if you go back to the model which we are talking, how did the model come up with positive diagnosis for a given blood sample, right? So this involves interpreting the important features for the model and how they interact with each other. So this understanding phase should ensure or will ensure that AI system is safeguarded against the data leakage and bias issues, right? So adding this interpretation. So rather than usually the earlier thing was after testing, if everything is right, we are directly deploying it. But here we are adding one more layer to this, that is adding something called an understanding layer, where it will clearly tell why the model has taken some decision, right? So how this to be done, that we'll see in the upcoming slides. Now, so the so for solution 1 and 2, both for data leakage and bias, this could be one thing. And for solution 3, it is all about explaining something, or the purpose of explaining phase is to interpret how the model came up with the prediction on new data in a production environment. Interpreting the prediction on new data basically uh, make help us to understand or expose that information if needed to the expert users of the system who imagine that somebody has challenged the decision made by the deployed model. So if you can explain why it has taken that particular decision, then that makes sense. So uh, by including the interpretation step, we were able to address the regulatory, or we will be able to explain or address the regulatory non-compliance issues which we earlier highlighted. So, so these two aspects. So why I have uh, shown all these things is that basically to tell that most of the ML models which you see, they are kind of black box models. So in other words, it is difficult to understand what goes inside a model. Sometimes it gives you really wonderful results, but you may not be able to explain why it is in this way and not the other way around, right? And also there is another aspect called monitoring, which can help you to kind of avoid this concept drift. So all these things usually comes under ML ops, but I'm just for the information, I've added this also here, right? Now, so usually what we have learned now is it is not just about uh, evaluating, or not just about uh, understanding that your model is efficient. It is also important to interpret or understand why the model has taken such a decision. So even before deploying, if you do that, then that can save you a lot of money. Because uh, if you think from an industry perspective, Failure of a model after deployment, that is a really costly affair. So if you have spent millions of dollars and you deploy that and then you understand this model is of no use, there are dozens of cases where such things have happened. So we'll quickly take a 1 minute break so that you can also take your eyes away from the screen. All right. So we have mentioned that consequences of poor predictions, it brings a lot of issues. So uh, like there's a necessity that basically if you know what is going inside, I'm sorry, if you know what you if you know what goes inside a model, or what happens inside a model, then that will help you to come up with better models. So there are a lot of things where which can uh, which directly tells what is the problem with the wrong prediction, right? So uh, so this is one of the aspects where the necessity of model explainability comes into picture. So whether it is about prediction or whether it is about classification, there are various rules or various examples where even big companies fail to achieve that, even after spending millions of dollars. So only at the end of that they realize that there is a lot of unfairness, there is a lot of there is a lot of non-accountability from a model prediction aspect, right? So because of these things, the reality is that you have data going into these black box ML models, and it is just predicting the when model is just predict doing something, and people have a feeling that as long as it is working fine, let it go. But most of the times, only after deploying that you get issues, and then you may have to kind of withdraw that particular model, right? So the usual thing is, if you are without machine learning model, you directly give instruction to the machine and it just follows. And once you have ML models, you have very fancy good results, and seem happy to that. But the moment you ask things like for example, you have a model and you ask, why did you predict the result as 121.56 and not anything else? So if the model has explainability flavor in the model, then the model should will be able to explain, hey, because of these reasons, this was found, and that is the reason why I have taken this sort of a decision. So in a nutshell, I can say that explainability is all about model transparency, design transparency, and algorithmic transparency. So explainability encompasses everything interpretability is. So the difference is that it goes deeper on the transparency requirement than interpretability, because it demands human friendly explanation for a model's inner workings and the model training process, and not just the model inference. So like if you talk about model transparency, being able to explain how a model is trained step by step, in case if you have weights in that, how the optimization method like minimize the errors in the model, or all these things are the model transparency. And when it comes to design transparency, you should be sorry, you should be able to explain choices made, such as model architecture, what are the various hyperparameters you have tweaked. And for instance, we could justify these choices based on the size and nature of the training data. If you are performing a let's say a sales forecast, and we know that our sales had a seasonality of 12 months, this could be a very good parameter choice. So if we had doubts, we could always use some well-established statistical method to find the right seasonality, right? So, and the other aspect is algorithmic transparency, being able to explain automated optimization. Say it could be hyperparameter tuning or grid search. So it could be any one of those, right? And uh, so ultimately to make the algorithms more transparent, right? Now, at least some of you might have a feeling like, what is the difference between these two terms, explainability and interpretability? So the, uh, the dictionary definition of the word interpret, it means to explain or present in understandable terms. So in the context of ML system, we add an emphasis on providing explanation to humans, that is to explain or to present in understandable terms to a human. So that is what interpret, the word meaning is. So, but in the context of ML and AI, explainability and interpretability are often used interchangeably. Of course, they are very closely related. It's worth unpicking the differences because things get complicated once you start digging deeper into these concepts. So interpretability is about the extent to which a cause and effect can be observed within a system. Or to put it in another way, it is the extent to which you are able to predict what is going to happen given a change in input or algorithmic parameters. So you can think that as a, you have a knob there and you turn the knob and see like, okay, if I'm giving this sort of a data, this could have been the prediction. So I'm able to look at an algorithm and say, yes, I can see what is happening here. On the other hand, explainability is the extent to which the internal mechanics of a machine or deep learning system can be explained in human terms. It's not about the decision, it's more about the algorithmic aspect. So it's easy to miss the subtle difference with interpretability, but you can consider it like this. Interpretability is about being able to discern or understand the mechanics without necessarily knowing why. Explainability is being able to quite literally explain what is happening. So you can think it in this way. Imagine that you're doing a science experiment at school. So the experiment might be interpretable to the extent that you can see what you're doing. But it is only really explainable once you dig into the chemistry behind what you can see happening. So you imagine that you are adding two salts and some acid and some sort of color is coming out. You can see what is happening. But if you want to interpret, you need to know, okay, I have added, say, sodium chloride and maybe another salt, and I have added sulfuric acid onto that. So basically, once you know the chemistry behind that, then that is known as uh, interpretability, right? So, uh, and also I can put it in a different way. Interpretability is the extent to which humans, including non-human, including non-subject matter experts, can understand the cause and effect and the input and output of a machine learning model. So, uh, and right. So interpretability means different things to different stakeholders. So if you think from a data scientist perspective, it means gaining a deeper understanding of how the model made a particular decision, which features are important, how to debug issues by analyzing cases where the model performed badly. So this understanding helps the data scientist to build more robust models. And from a business person or business stakeholder perspective, it means understanding how the model made a decision so as to ensure fairness and protect the business users like that brand value, right? And for the end user, it means understanding how the model made a decision and allowing for meaningful challenge if the model made a mistake. And from a regulatory compliance point of view, it means auditing the model and AI system, following the decision. Like when things go wrong, it is in that aspect only this has more relevance. So there are dozens of interpretability techniques available out there, and uh, we don't have time to go into all the aspects. But just to give an understanding, one of the most common techniques is basically something called the post hoc interpretability techniques, where you build a model, you finish the training, and then you apply these sort of techniques for usually most of the deep learning as well as complex ML models, we make use of uh, these post hoc techniques, post hoc interpretability techniques. And there are intrinsic techniques for models that are inherently transparent. For example, if you take a decision tree classifier, so right from that decision tree, you will understand on what all basis the model has taken that decision. And also there is another classification. There are some interpretability techniques which you can apply across all models. So those models are known as model agnostic techniques. So techniques that are independent of the model. While you have another set of techniques that are dependent on the model. And there is also another classification. There are interpretability techniques which, say for example, you take one specific instance from the data, and then you try to understand on what all parameters this particular model has predicted this sort of a result. So such kind of a local interpretability techniques are there, and you also have global interpretability techniques, which means that as a complete data set you perceive that, and then you try to understand on what basis the model has taken that particular decision, right? So uh, there is a lot of significance for these interpretability as well as explainability, especially when it comes to research. It's all about reproducibility. It is very essential to prove any sort of scientific method, and also statistically grounded optimization methods is desirable when causality needs to be proven. So in that aspect, explainability has lot of significance. And when it comes to clinical trials, you must be able to reproduce findings, and it should be statistically grounded. And say for example, especially if you are using AI or ML models in very uh, critical application like health analytics and all, there is a concern of life and death concern, right? So similar to clinical trials, here also you need to have that transparency on like how something is being done. And also from a public policy or governance perspective, where for example you have something to be done by an AI, where an AI takes a decision. In that aspect also, explainability plays a very significant role, right? And in general, when you see different models which are simple in nature, their of course accuracy could be little low, but their interpretability is always on a higher side. So very highly accurate models or nonlinear models usually, uh, their accuracy is more, but the level of interpretability or how you can interpret that is again a difficult task. But of course there are techniques and methods to do that, which we'll see in a little while. So usually we say that good explainable systems, they has these aspects. So which means that imagine that you are trying to uh, do some prediction for the presence of diabetes. So which means that the measure of blood glucose level has a direct relationship. So which is consistent with prior human beliefs. So if the blood glucose level is higher than usual, this might indicate diabetes for the patient, although diabetes is not necessarily high blood glucose levels can also be momentary, and high blood glucose level doesn't always mean that patient has diabetes. But as the explanation is consistent with the prior knowledge, end users will have more trust in such explanation. Just to give a understanding of what this point one means, right? And the other aspect could be fidelity, where providing a holistic explanation is a truthfulness of the explanation, which is also like termed as fidelity of ML models. So explanation with high fidelity can approximate the holistic prediction of the black box models, where low fidelity explanation can interpret a local data instance or a specific subset of the data. So imagine for doing sales forecasting, providing explanation based on just trend of historical data doesn't give a complete picture, because there are other factors such as production capacity, market competition, or customer demand, which might influence the outcome of the model. The other aspect will be abstraction, because human friendly explanations are always expected in a concise and abstract format. too many complicated details can also impact the experience of end users, right? So imagine that if a model predicts for weather forecasting, if a model predicts high probability of rain, the concise and abstract explanation can be that it is cloudy now and raining within 5 kilometers of the current location. So there is a high probability of rain. But if the model includes details related to precipitation level, humidity, wind speed, which might also be important for the prediction of rainfall, these additional details are complex and difficult to comprehend and hence not so human friendly. So good human friendly explanations basically include the maybe appropriate amount of abstraction to simplify the understanding for the end user. And then you have the contrastive explanation. Say, for example, um, if a model predicts that the employee is likely to leave the organization, and then contrastive explanation try to justify the model's decision by comparing it with an instance prediction where the employee is expected to stay in the organization and compare the values of the key features which is used to model that data. So later in the hands-on session, we'll see these kind of aspects in a much detailed way. And uh, lastly, it's all about social aspect, where the model explainability determines the abstraction level and the content of explanation. For example, suppose a stock predicting ML model designed to prescribe actions to user, it suggests that suggests shorting a particular stock. So in that case, the end users outside the finance domain may find it difficult to understand. But instead, if the model suggests selling a stock at current price without processing it and buying it after 1 month when the price is expected to easily, but uh, so the good explanation consider the social aspect and often user-centric design principles of human-computer interaction need to be utilized basically to design good explainable ML system, which kind of will make the society a lot more better. So how do we start into this explainable AI aspect? So I'll just put that, sum it up with a Venn diagram. So you have these three domains: human-computer interaction, AI, and then social science. So when we talk about XAI, it's not just limited to an agent revealing its underlying causes or another agent's decision. So the solutions for XAIs are more of a human-agent interaction problem. So what we see in this Venn diagram is the influence of social and philosophical aspects of AI solution, as well as our interaction with it. So just to say that our explainable ML and interpretable ML is a subdomain of this XAI, and XAI seeks to explain why a certain observation or event has happened. The user cannot understand the model's behavior uh, or decision unless they know the basis of the decision. So assume a trained model that accurately labels images of anthropods based on features like number of eyes, legs, wings, and presence of compound eyes and stinger. So on what basis is it making a decision? So that basically the uh, the common man or the user should know, because research shows that people have certain cognitive biases caused by their beliefs or roles that they apply to explanation generation, selection, and evaluation of these models, right? So this is what earlier I was talking. There are a lot of interpretability methods. We'll not go into all of that, but certain aspects we'll try to understand. So even if you, for example, if you are trying to build a model which can classify these and say whether whether the particular anthropod which is shown here, whether it belongs to the class of anthropod, right? So you have features like legs, stinger, eyes, compound eyes, wings, etc. So now as a user, you would like to understand the labeling behavior through an explanation agent. So imagine that you are asking, uh, so why is the image one? So over here, it is labeled as a spider and not as a beetle. So then uh, you can expect the answer that, see, that anthropod has 8 legs and it has consistent, which means that it is consistent with the category of spider. That is the reason why it was classified into that particular class, right? So explainable AI is therefore not just a presentation of associations and causes. It is driven by a need for context-based, need for context on facts the explainer chose to focus on. So basically, the answer could be a kind of the reasons on what all reason it has kind of uh, decided that it should go into this particular category. And now, so what are the different aspects which is actually kind of required, or which is kind of basically is a reason why you have a lot of significance for explainable and interpretable ML models. So uh, one aspect is of course transparency, which means that do all stakeholders understand the model decision in terms of format and language. And the other aspect is called causality, so which means that whether the predicted changes in the output due to some change in input will also occur in the actual system. Earlier, I mentioned about a knob where you can turn it and see, okay, if the data was of this sort, maybe it would have given this sort of a prediction. And also privacy and fairness, whether it could be verified that the model decisions are fair over maybe protected groups, or maybe in the given data whether it has got uh, any sort of bias issues, right? And also it increases the trust as well as usability, which means that how capable is the system to provide a safe and effective environment for users to perform their task. And also it increases the reliability of the model. So how robust is the system performance against a change in parameters and inputs? So usually, whenever you have a model, usual ML engineer, once he creates a model, he tries to evaluate the metrics. So imagine that if he's doing a classification task, he'll try to understand whether the model is good or bad using these parameters, the common parameters. Now, if he's going for a regression task, then he might go for a mean square error or a root mean square error. So usually this is the trend. Now, there is also a hype cycle for predictive models. So which means that initially everybody likes to predict things, right? Even right from childhood, we always have a curiosity to know about the future. So I need a predictive model, and you decide to learn one programming language, either R or Python or any sort of thing, and you build your first ML model. So at that point, you have an expectation that like, wow, ML is so easy. Okay, it is only this much, and why the people have this much hype about machine learning. And after some time, once you start working on ML models and once you start deploying it for real use cases, then you realize that, oh my God, my model is not working on the new data. So it is this point, there is an increased significance where people try to have an idea and they realize that I need to understand the model. So it is in this context we always talk about XAI. So as already mentioned, there are different ways in which you can kind of categorize that. There are different sets of taxonomy for XAI, but we'll be looking at only very maybe 3 or 4 aspects about that, not all the aspects. So usually we divide, for example, you have a model and you try to divide that from an instance level and you try to understand what if like the data was this and then like what could have been the predicted the output, or what could have been the prediction. So this helps to debug a model and understand whether the model is right or wrong. So instance level exploration methods help us to understand how a model yields a prediction for a particular single observation. And now imagine that you want to completely understand the data set. So usually you call this as an auditing the model, where you you understand the overall behavior of the model, right? And we'll do all these things in the hands-on. So all these aspects which is shown here, we will try to do in the hands-on. So maybe I'll just go to that directly. Just a second. So already you were given two different links. So the second link, if you uh, click on that, you should be able to see this sort of a screen, right? Posit.cloud. You can just, if you have already signed up, you can just log into that. So I'm just logging in. Just a second, I'll just log in. So once you log in, maybe it'll take few seconds to load. So you can click on a new project, and here I have a new RStudio project, right? So till this page, once you sign up, you should be able to reach. And there is also another link which has this sort of a content, which is a yeah. So basically, this will we'll try to build a model, and also we'll try to understand the interpretability and explainability aspects of that particular ML model, right? So we have hardly 15 to 20 minutes, so I'll just rush up and show you certain aspects. So what I'm going to do, it is already available in the handout or the first link which I've shared to you. So here I'm going to create a new RStudio project. And what we're going to do is we will try to do some sort of a regression task and build a model basically for that. And then we'll try to understand what is the problem for that particular model. And once you include explainability and interpretability onto that model, what all other things you can infer from that particular model, right? So you have to install certain packages, but right now, I think already in my console, already it is installed. So I'm just calling a library called okay, it is not installed. So I may have to first install that. So I'm just copying and pasting. There are certain aspects which, especially these dialects package and all, it is available in Python also. But there are few things which is not available in Python. That is the reason why I have convert or I have put this whole thing in R. So once it is installed, just like in Python, if I'm not sure how many of you know Python, but you can again, once you install the packages or library, you have to call those library. So right now it is getting installed. Yes, I think it is installed. So just to make sure that it is installed, I'm just calling a, so it is installed and the other libraries also. So whatever that is in the other handout, from that I'm just copy pasting, right? So all these libraries have been called onto the console. So now let me just zoom in so that you can see better. So we'll try to understand a data set. So here some of the some of the data sets comes with inbuilt data set. So there is a data set with the name World Happiness Report. So I'll just see happiness. This is a data set with, by default, it comes along with one of the package called Model Studio, which we have already installed. So this particular uh, data set is all about uh, World Happiness Report, which is a landmark survey of the state of global happiness. So first report was published in 2012. What you see on the screen, I think it is a report from 2015. So the happiness scores and rankings use data from a kind of poll, and the scores are based on the answers to the questions to people, and basically it tells whether a particular person is happy based on the score. So the score is calculated from all the other 7 variables: GDP per capita, social support, health life expectancy, freedom of life choices, generosity, perception of corruption. So using these different variables, it has calculated the score, happiness score. So our goal is to build a model which can predict the happiness score if we give the other data. So that is going to be our task, right? So you can see in that first link what I've shared, model building for regression task. So here what we are going to do is we will build a model which will help us to predict this happiness score. So happiness score, so you can see here there are two sort of data set. Usually for building a model, you need a training data set as well as a testing data set. So here by default, both training and testing data set, it is available within that particular library, right? So now what we're going to do is we are going to build our first model. So I'm just naming that as my first model. And I'm going to build a random forest model. So already, if you remember, I have a library called Ranger, and this library helps me to build a random forest model. So I'm just calling the Ranger function. And if you remember the very initial thing, what I've mentioned is it's all about giving a formula to your model. So here, my response variable, what I want to predict is nothing but happiness score. So I'll just say score, and whatever that is on the right hand side of this tilde operator, those will be my explanatory variables. So I can put any variables of my choice: GDP per capita, plus maybe healthy uh, life expectancy, plus freedom life. I can even give all the 7 parameters. It's up to me to decide, right? So, and data, I'll say it is happiness underscore training data I'm just making. So if I've done everything right, yes, I didn't get any error, which means it is executed successfully, right? Now, I have this model, which means that I have a kind of black box there. Now, I need to basically do the prediction, right? So the model is used to kind of do the prediction on the testing data set. That's what I'm going to do. So my first model result, that I'm just making use of the predict function. I'm not going into explain how this happens because of time constraint. So my first model, and I'm asking, hey, you do that in happiness underscore test, right? Now, so if I check what is inside this my first underscore result, just to view that, it says that I have 3 variables and total of 156 rows. So the training data set had around 625 rows or 625 entries, and the testing data set had around 156 rows. So if I want to know what are the prediction, so here for all the 156 rows, it has predicted the happiness score based forest model, and it has predicted the value for all these 156 rows, right? Which is my testing data set. Now, how do I know that whatever that is predicted, it is the right thing? So for that only, we already have something called the ground truth available here. Because if you know, if you check here, if I want to view happiness underscore test, I have these 156 rows here, and here already the score is predicted. Now my task is to compare that with the value whatever that I got it as prediction. So here I can just, since it is a regression task, I can go for a mean square error or root mean square error. So I'm just going for a RMSE, root mean square error. Here I would say, hey, please compare happiness underscore test dollar score, which is the actual value, with my predicted value. So my underscore first underscore model underscore result dollar predictions. It has given me some value like 0.6600, right? So which means that I got the root mean square error as 0.6. So right now we have built only one model. I can build dozens of models like this, because what I have to do is I just have to change this particular formula, right? Now, what if I'm gonna build, or again, I'm gonna build a model with the same formula, and again, I'll try to see what is the root mean square error. So here I'm just building my first model, just renaming that as 2. My first model, but second iteration I'm just trying. Okay, so I have built that, and the second iteration result I'm storing in result 2. And here my this thing got wrong. That's why my first put 2. So now if I find the RMSE value, you can see I have used the same set of the same set of formula, same data, but the first time I got RMSE value of 0.6600423, but in the second, when the second time I'm running, I'm getting a different output. So this is what I have been talking about. Like, you can have different sort of output each time when you run. So this is why all ML models has uncertainty and kind of bias inherent in all these models. Now, if I change uh, this particular formula, then I may get a different answer again, right? So ultimately, one thing is that I have a lot of uncertainty and randomness embedded into these things, but I don't know what exactly is happening there, right? So now, how do I incorporate explainable AI into this regression model? So for that, you have something called explainer. So it is part of Daleks package. So just to save time, you in the handout given, you can check the title, incorporating XAI into regression model. I'm just pasting that as it is, just to save time. So it says that it has created a new explainer. So what it is all about, there are a lot of things being shown here. Instead of going through that, I can even make a small dashboard for that, just with one line of code. So I'm just zoom out so that the dashboard comes correctly. So it is saying that it is creating some dashboard. So if everything goes right, I should be able to see the dashboard. So the same you can see in the handout also. So maybe it'll take a few more seconds. Yeah. So this is the dashboard it has created. So which means that, okay, if I zoom, that is going out. 1 second. Yeah, just to show that, I'll show from the handout itself, because when I'm zooming, it is going away. Yeah. So here, for example, if you notice here, I have a dashboard. So imagine that I want to understand how GDP per capita for a specific instance in the data. how it is being changed. So if I'm changing, see again here, health life expectancy for a, okay, I'll show from the other place itself. 1 second. So ultimately here you have an interactive dashboard where you can change things and understand like why something is this way, not the other way around. So we'll wait for a few more seconds for that to come up. Yes. So here I'm just changing the health life expectancy and your thing. And if I want to know the on what basis the model, I want to know the perception of corruption of South Sudan, on what all basis the I'll add one more aspect which will give you more here. Yes. Yes. So here, if you see, this is something called uh, ceteris paribus. So this is a measure which kind of tells you, see, right now, my particular value or the data value is here. If the data value was over here, right? So for, you have a sort of graph here. If it was here, then how the prediction would have been. So like that, a causality analysis can be very easily done on this. Now, if you want to do that for multiple variables, then you have another thing called uh, over here, something called a partial dependence, right? So there are a lot of aspects to this. So few things I'll just show you. So uh, this thing, which is known as ceteris paribus profiles, that show how a model's prediction would change if the value of a single exploratory variable changed. So this is more often known as CP profile, and the graph you show here is on a different data set. But still, one thing is that the main goal is to understand how changes in the values of variable affect the model's prediction. So for instance, here it is from a Titanic dataset, a passenger Henry, a 47-year-old man who traveled in the first class. So what if his age was more than this? Then what was the probability that he would have survived? Right. So like this, a lot of what if analysis could be done very easily on this sort of a metric. Right. Again, another CP profile. Now, this is, as I mentioned, it's for in an instance level, but if it is on a data set level, then you have uh, things like breakdown values. So for example, prediction of this sort, what all values has contributed for that prediction? Very clearly, it actually shows. So once we calculate model prediction, the question often arises is that which variables had the greatest impact? For linear models, it is easy, but for non-linear models, it is a little difficult. So for that, you have also something called the shapely values. So shapely values are the most popular agnostic method for non-linear models, especially. So it is also very much related to game theory. I'm not going into the concept exactly. Just want to say that there are a lot of techniques available which can show the interpretability or explainability of a model. And many models have built-in ways of assessing the importance of variable, but variable importance is basically the permutation importance of a variable. It is basically the difference between model performance of the original data and the model performance measured on data with the permuted variable. Now, partial dependence plot, I have already mentioned. It is often useful for comparison of different models because some models could be flexible than the others. So if I want to know, I have multiple variables and on there I have to do a causality analysis. So now the data point is here. If the data point was a little down here, what could have been the prediction? So like this on a scalable basis, if you want to do, you can go for this partial dependence profile. So uh, it is based on the age. What if somebody's age was less than this, or what if somebody's age was more than this? Then how the model prediction would have varied, that very clearly we'll be able to tell, right? Now, the other aspect is there are this is actually a large sea out there. We have just kind of taken few drops from that sea in this session. So which means that there are models which are interpretable by design, especially as I earlier mentioned, like decision trees and all. And there are model specific methods to find out the interpretability or transparency of a model. And there are also things like, as I have already mentioned, like PDP, partial dependency plot and all, which kind of explains why the model has taken such kind of a decision. So the hands-on sessions was basically using these packages, and the main package was Dalex. Dalex package is also available for Python, but the dashboard which you have seen towards the end, that aspect is not available in Python. So that is a reason why this whole hands-on session I have put it into in basically in R programming, right? So if you have any specific queries related to the session, I'll be really happy to take those questions.
Participants, please write your queries in the chat box, or otherwise, please unmute and ask regarding the session. Otherwise, you can talk with the speaker regarding this session based on your feedback. I think it is a useful and an eye-opening session for I got few comments personally itself. It will be a great eye-opening session for them. So please write your queries in chat box and also unmute and ask your queries. Then it will be then only it will be a good uh, interactive session, Q session and all. Yeah, I have a question in the chat box. Yeah, I mean, sir, how to analyze the explainability or interpretability of an RL agent? One of the question received from Navneet.
Yeah, so basically in reinforcement learning and explainability, interpretability, I haven't worked in that, but both, irrespective of whatever is the kind of technique for basically ML technique, you have some methods which can be applied across all the models. So irrespective of whether it is a neural network or a reinforcement learning, like I've mentioned about agnostic methods. So any such method could work well in RL also. But frankly speaking, I haven't worked with the explainability aspect of RL, but I have worked with ML models as well as most of the deep learning models. So in that aspect, these agnostic methods work well in those scenarios. What is the best book for mathematics for machine learning right now? Maybe if you can understand the basics of linear algebra, that should be good to start. So rather than a book, maybe I can suggest one YouTube channel which kind of uh, gives you really good insights about the mathematical aspects, especially in a very in the best interesting way. So I'll just put that link out there, which gives you a lot of insights about the mathematical aspects in a wonderful way. How explainability, interpretability effectively used for user experience designs. So are you I'm not sure. I think you are asking about the human computer interaction, HCI. Is it? Okay, that human. So yeah, so if you remember earlier, I've shown a slide with a Venn diagram. So here actually it is definitely from that design point of view. Maybe I'll just go back to that slide so it'll be easy for me to talk. So if you remember this particular aspect, so all these technology, even though we are saying that once that super intelligence comes into picture, you won't have human in the loop, but that may take a lot of years for it to become a reality. But till that time, always it is assumed that you have AI and also you have human in the loop. So it is from that aspect, whatever you create, you need to have this human computer interaction. So that is actually the reason why all these immersive technologies, AR, VR, it has a lot of significance because it gives an experience in such a way that like you are within that. So that aspect is basically focuses on the as it was mentioned, focus on the interaction between humans and computer, basically creating a human centric technology, right? Uh, is POSIT a new, I mean, new learning for me? Can you explain a bit more on that? POSIT is basically the previous RStudio. So you can even download that and do. But since this was an online session, I thought it is easy to go with that web-based interface, which means that you can do everything within the browser. So uh, i- for I think for 50 hours in a month or so, like it is completely free. Only if you want to use beyond that, you need to pay for that same platform. Can we deploy a trained agent which continuously evolves after deployment? How feasible is it? That is actually it is not very easily possible. That is the reason why you have things like or subdomains like MLOps. So MLOps is a very interesting domain where you focus on things that like after deploying what all things I should do to my model so that the model stays relevant. So that has got a lot of significance. So, so output is not the same always. Can we not apply it for real-time critical? No, Asha has asked a question. So you're saying like, so then how can we rely the model? So in order to make these models reliable, there are things like cross validation. So as I mentioned, you run that uh, maybe a 40 50 times, and in that whatever maybe you are getting as the average, that the kind of usually in a, when you are dealing with a real problem and you want to really deploy something, in those cases you may have the training data set not as a static training data set. Each time the training data set also varies. So once you have an average of all these things, then you could have a reliable reliable system. So there are various aspects to that, as I mentioned, like cross validation is there. Then there is something called in order to know whether your model is overfitting or underfitting, there are various aspects. So uh, using all these things, we can go for a decision whether it is good or bad. But still, whatever we do over there, nothing can be kind of quantitatively tell us that the model is not fair or the model is not transparent or the model is not accountable. So those kind of things, uh, we need explainability and interpretability. Yeah, Vikashini, good to know that.
Is there any other queries from the participant? You can unmute and ask. And this kind of QA session that I wanted throughout the workshop, but I quite disappointed from the first 2 days. there is no effective QA session after the session. So first time I am pretty much happy with that. You are engaging with that QA session. So thanks, Ebin, too. Yeah. Yeah. So, is there any other queries from the participants? Yeah. Thank you, Ebin. We can wind up.
Yeah,
Uh,
yeah, yeah,
Yeah, thanks
yeah.
for the
And thank you.
despite with your busy schedule and all, difficult to catch you and also at that time. So thank you, thank you with for supporting with us for this.
Yeah, not a problem. Yeah, the pleasure is mine. Actually, a lot of good questions came, and also the participants are really wonderful. I've put my email ID there in case if somebody wants to get in touch
Yeah,
with me, they can drop an email. Yeah,
yes, yeah.
yeah. Thank you, and have a great day.
Thank you, Abin. Thank you, participants, for this wonderful day. Thank you. Have a nice day. Bye bye.